Welcome to CBSEasy.
Getting ready for your exams? If you're tackling polynomials, you are in exactly the right place. In the next few minutes, we're going to solve 8 key problems, step by step, just like you'd see them in your textbook. Think of this as your quick-fire revision session.
Okay, so here's the game plan. We'll start with the visuals, how to read graphs and find values. Then we'll get into the really cool relationship between zeros and coefficients. And we'll wrap things up with a look at some core properties and polynomial division.
All right, let's jump right into our first section. This is all about getting comfortable with the basics, seeing what a graph is telling us, and doing some straightforward calculations. So first up, a classic graphical problem. It's pretty simple on the surface, but it's really testing a core concept. How do you figure out the number of zeros just by looking at where the graph goes?
And you know, the secret to this is incredibly simple. The number of zeros a polynomial has is literally just the number of times its graph hits or crosses the x-axis. That's the whole trick.
So, because the problem tells us the graph crosses the x-axis at 3 different points, the answer is 3. The polynomial has exactly 3 zeros. It's a direct one-to-one relationship.
Okay, moving on to our second problem. This one is a simple plug and play. They give us the polynomial, and they want to know what its value is at a very specific point, when x is equal to -1.
So how do we do it? First, we just swap out every x with a -1. That gives us -1 squared minus 3 times -1 minus 4. Now we just have to be careful with the signs. -1 squared is +1, and -3 times -1 is a +3. So now we have 1 plus 3 minus 4. Do the math and you get 0. And hey, here's a little bonus tip. Anytime the value of a polynomial is 0 for a certain x, that means x is a 0 of the polynomial. So we just proved that -1 is a 0.
All right, now that we have the basics down, let's dig a little deeper. We're about to uncover a really powerful shortcut, a hidden connection between the zeros of a polynomial and the numbers or coefficients that make it up. This is a real game changer.
You are going to see this kind of question all the time on exams. They're asking for the sum of the zeros, but here's the kicker. You don't actually need to find the zeros themselves to answer it.
The trick is this handy little formula. For any quadratic polynomial that looks like ax squared plus bx plus c, the sum of its zeros is always just -b over a. So for our problem, we just need to identify a and b. A is 1, b is 7. So the sum is -7 over 1, which is just -7. See, we solved it in seconds. No factoring required.
Okay, so what if we flip that idea on its head? This time, they're giving us the sum and the product of the zeros, and our job is to work backwards and build the actual polynomial.
Well, there's a formula for this too. It's like a recipe. The polynomial is always x squared minus the sum of the zeros times x plus the product of the zeros. We were given the sum is 4 and the product is 1. We just slot those numbers right into our recipe and boom, we get x squared minus 4x plus 1. It's really that straightforward.
Oh, I like this one. It's a bit of a puzzle. It gives us this really specific condition. The 2 zeros are reciprocals of each other. That little clue is the key to cracking the whole thing.
Okay, think about this. What happens when you multiply a number by its reciprocal, like 5 times 1/5? You always get 1. So if the zeros are reciprocals, their product has to be 1. Now we also have a formula for the product of zeros, right? It's c over a. For our polynomial, c is k and a is 2. So we can set up an equation. K over 2 must equal 1. A tiny bit of algebra, and we find that k has to be 2.
All right, let's head into our final section. We're going to tackle some of the deeper concepts now, starting with the very definition of a polynomial, and then moving into a couple of problems that involve division.
This is one of those questions that checks if you know the fundamental rules of the game. What actually makes an expression a polynomial? We're looking for the one that breaks that rule.
So here's the absolute #1 rule you have to remember. For an expression to be a polynomial, all the powers of the variable must be non-negative whole numbers, 0, 1, 2, 3, and so on. The instant you see the variable x sitting in the denominator of a fraction, like in option C, it's a disqualification. That implies a negative exponent, which is a big no-no for polynomials.
Here's another exam favorite. When you see that phrase exactly divisible, a little bell should go off in your head. It's a huge hint that we need to use something called the factor theorem.
So the factor theorem is our best friend here. It says that if a polynomial is divisible by x plus 5, then that means -5 is a 0. And if -5 is a 0, then plugging it into the polynomial has to give you an answer of 0. So that's what we do. We substitute -5 for x all the way through. It's a bit of number crunching for sure, but once you calculate everything and simplify it down, you're left with a very simple equation. 80 plus k equals 0. And from there, it's easy to see that k must be -80.
And for our final problem, this question sounds really complicated, asking what you have to subtract. But here's the secret. It's just a fancy way of asking, what's the remainder? The whole idea is that the remainder is the leftover bit that stops the division from being perfect. So if we just subtract that leftover part, the division will work out exactly. To find that remainder, we have to roll up our sleeves and do polynomial long division. And when we do, we find out the remainder is 14x minus 10.
So the thing that needs to be subtracted to make the division perfect is simply the remainder we just found. The final answer is 14x minus 10.
And that's it! We just blasted through 8 essential polynomial problems. Let's do a super quick recap. We learned that zeros on a graph are just the x-axis intersections. We practiced direct substitution. We used the powerful sum and product formulas. We even built a polynomial from scratch. And we saw how the factor theorem and finding the remainder can solve those tricky division problems.
We've focused a lot on quadratics, but that leaves us with one final thought. What about bigger polynomials, like cubics? Well, the cool thing is, these same ideas still apply. There are relationships between the zeros and coefficients for cubics too. They just get a little more interesting. That's something for you to explore next. Thanks for tuning in, and good luck with your studies.
Thank you for watching with us. See you next time.